Hello everyone, my name is Francisco Pereira. I'm a PhD student from University of Lisbon, and I'm happy to present our work on automatic parallelization of software network functions. This is joint work with my advisors, Professors Pedrosa and Fernando Ramos. So middle boxes or network functions are pervasive in today's networks. They implement a wide range of core functionality, for example, load balancers, firewalls, deep packet inspectors, and rate limiters. Although these were originally implemented using fixed function closed source appliances, there was a transition to using commodity off-the-shelf servers. And this came with lower costs, easier management, and faster development cycles. However, it came at a steep cost, performance. And the performance cost is exacerbated by the fact that CPU improvements over the years haven't really been keeping up with the evolution of line rates throughout the years. So for example, there was a time when 1 gigabit per second links were the norm and we could use one CPU core to handle them just fine. And then 10G links became the norm and one CPU core could barely handle them. And nowadays we're talking about 100G links, which we have no other choice but to resort to multiple CPU cores to handle them. And the problem becomes even worse when we think about the future coming 400 and even 800G links. So there's really no way around this. We really need parallelization on our network functions. So this begs the question, how do we typically parallelize a network function? Typically, we parallelize a network function by running the same network function instance on each core and having the NIC receiving traffic and distributing this traffic among those cores. Here we represent packets accessing the same state or belonging to the same flow with the same caller. And because cores can receive packets from any caller, they really need synchronization to this shared state that persists across packets. But this is a problem because when we're dealing with 100G links, we really have only tens to hundreds of nanoseconds of processing time per packet, which we cannot really meet if we are dealing with 100G links and with synchronization. So we really need to avoid inter-core coordination and to achieving high performance in parallel implementations. What we want to do is actually find a way to carefully partition traffic among cores so that every packet finds the state that it needs to on that local core, and therefore cores have no need to share state amongst themselves, and therefore no need for synchronization. But this is easier said than done. Actually, parallelization is a very hard thing to do. And to illustrate why parallelization is hard, let me give you an example of a firewall. So our firewall is a network function that sits between a trusted LAN and an untrusted WAN. Imagine that Alice on the LAN wants to communicate with Bob that is on the WAN. So Alice's packet is intercepted by the firewall, which stores the information that Alice wants to start a conversation with Bob and forwards the packet to Bob. Later, Bob replies to Alice, and this reply is intercepted again by the firewall, which double checks that it's in fact a conversation that was started by Alice and forwards the reply to Alice. Later, if Trudy wants to send a packet to Alice, the firewall intercepts and drops this packet because Alice has no ongoing conversations with Trudy. So back to our question, why is parallelization hard? So first of all, we need to know how to correctly partition state across cores in order to avoid synchronization altogether if possible. This is called sharding. And in the case of our firewall, there's a hint of symmetry in how this should be done. That is, packets from Alice to Bob and from Bob to Alice should be sent to the same core in order to avoid synchronization. But this quickly becomes very complex when you think about more complex network functions. The second reason for why parallelization is hard is that even if we know how to shard state to avoid synchronization, we need to know how to correctly forward packets to cores in order to enforce the sharding solution. This distribution of packets among cores is done in the NIC by a process called receive-side scaling, or RSS for short. This process runs for every single packet and extracts a configurable set of packet fields from every packet, feeds them to a hash function, which combines them with a configurable key, which then outputs a hash that is then used to infer to which core to send a packet to. Now the question is, how can we configure this mechanism, or more specifically, what are the keys and packet fields that enforce our required sharding solution? And finally, which is kind of obvious, but parallelization is hard just because in the end we need to write performant parallel code, which is filled with pitfalls and traps. Just to name a few, for example, false sharing, which can be solved with cache alignment, concurrent memory accesses, which can be solved by synchronization, load imbalance, which can be solved by load balancing, just to name a few. And worse than all of this is that if you want to modify your network function or add a new feature, you need to go back and readdress all these challenges again. We argue that parallelization should not be done manually. And exactly because we're dealing with a very constrained domain, the NF domain, the typical constraints found on network functions are exactly what makes them amenable to parallelization, specifically automatic parallelization. So in this slide, we propose Maestro, a solution for automatic parallelization. Maestro offers a push-button parallelization abstraction to the developer. It favors shared-nothing architectures, but provides a highly optimized log-based alternatives for when shared-nothing is just not possible. It can also generate parallel implementations using hardware transactional memory. There are 3 key ideas supporting Maestro. The first one is to use static analysis to infer how the NF keeps and maintains its state, and therefore inferring a sharding solution that avoids synchronization. The second one is to formulate this sharding problem as an SMT formula, feed it into an SMT solver, which then gives us the NIC configuration that enforces the sharding solution. In the end, we can grab the products from the previous 2 insights to completely automate code generation. This is what Maestro's pipeline looks like. We start by receiving an implementation of a sequential network function. This implementation is fed into an exhaustive symbolic execution engine, which is responsible for generating a model of the network function. This model is fed into the constraints generator, which is responsible for finding the sharding solution that allows for shared-nothing architectures. This sharding solution is fed to the receive-side scaling configuration finder, which is responsible for finding the NIC configurations that enforces a sharding solution. And both the NIC configuration and the NF model are both fed into the code generator to finally generate the parallel implementation. So let's start at the first stage of this pipeline. And grabbing our firewall example, we feed our sequential code of our firewall into the exhaustive symbolic execution engine, which gives us a sound and complete model of it. One of the main challenges of exhaustive symbolic execution is scalability due to path explosions. But fortunately, because we're dealing with a very constrained domain, the NF domain, this is actually tractable. And our NFs have similar constraints as the ones found by using frameworks commonly deployed as frameworks as eBPF. So this is a depiction of the model of our firewall example. It starts by asking if the packet came from the LAN or came from the WAN. If it came from the LAN, then it stores that flow information using a map and forwards the packet. This is what happens to Alice's first packet. If the packet came from the WAN, then it checks if the inverted, the symmetric flow information is stored on that map. If it is, forwards the packet, which is what happens to Bob's reply to Alice. If it does not find it, then it drops the packet altogether, which is what happens to these packets. So when thinking about parallelization, only really the stateful operations pose a problem. So because our firewall uses the map data structure, we need to carefully think when is it safe to concurrently access a map without using synchronization. So our goal is to partition the map across cores without using synchronization. And to do this, we provide 5 insights on how this could be done. In the interest of time, I'll only be addressing the first 2. I invite you to read our paper to find out more about the other ones that basically deal with the hardware limitations. So the first insight is quite simple. Imagine that you have a network function that uses a map to update its state and uses as key the flow information. This could be, for example, the 5-tuple. So the insight is that access with the same key actually trigger accesses to the same state. Or put in other words, for our example, packets of the same flow access the same state, so they should be sent to the same core. And from this insight, we have a constraint, we generate a constraint that every pair of packets must be sent to the same core if they belong to the same flow. That is, if they have the same flow information. The second insight is called subsumption. Imagine that you have a network function that actually performs 2 map operations. One uses both the source and destination addresses as key, and the other one uses just the destination address. So notice that packets having both the same source and destination address, they will always have the same destination address and therefore should be sent to the same core. The same cannot be said about packets having only the same destination address. They might differ in the source information. So actually sending packets with the same destination address to the same core will necessarily send packets with both the same and different sort information to the same core. So in this sense, we say that the constraint on packets having the same destination address subsumes the other constraint on having both the source and destination addresses being equal. So here we generate the constraint that packets with the same destination address should be sent to the same core in this scenario. So let's get back to our firewall example. Recall that it used 3 different map operations using different keys. Maestro uses the key quality insight to infer that packets coming from the LAN should be sent to the same core if they belong to the same flow. Similarly, for packets from the WAN, Maestro finds that packets from every pair of packets from the WAN should be sent to the same core, again, if they have the same flow information. And bringing this all together, Maestro finds that packets from the LAN and WAN should be sent to the same core if they have symmetric flow information. So now we have our sharding constraints. It's time to find the right NIC configuration that enforces them. Recall that the RSS hash mechanism is configured with both a key and packet fields, and that the hash is used to decide to which core to send the packet to. So every pair of packets that generates the same hash will necessarily always be sent to the same core. So the question is, can we make it so that every pair of packets that satisfies the constraints or sharding constraints generate the same hash and therefore are sent to the same core? Is there a key to do this? Is there a key that enforces this? So we formulate this as an SMT formula, as an SMT problem, feed it into an SMT solver, which gives us exactly the NIC configuration that allows us to do this. In the end, at the end of our pipeline, we just grab our model and our NIC configuration, and in a matter of minutes, we generate the final parallel implementation. Sometimes shared nothing solutions are really not available. For example, our SMT solver can deem the problem unsatisfiable. In that case, we provide you with a read-write lock-based solution that as an alternative to the shared nothing architecture. We invite you to read our paper to find out more about our lock-based implementation. So really, because we're promising automatic parallelization, the most important question is how does the parallel network function generated by Maestro scale with the number of cores? We evaluated 3 different parallelization technologies, all automatically generated by Maestro: a shared nothing technology, a locked-based solution, and a hardware transactional-based solution. We evaluated them against varying traffic patterns, packet sizes, and churn amounts, and compared them with the vector packet processing framework. In the interest of time, I'll only be addressing the parallelization technology's scalability. Okay, so let's take a look into scalability. On the right side, on the y-axis, we have all the network functions that we evaluated. We have a baseline no operation, a static bridge, a dynamic bridge, a policer, a firewall, a network address translator, a connection limiter, a port scan detector, and a load balancer. On the x-axis, we have the number of cores from 1 to 16 cores. On the y-axis on the left side, we have throughput in millions of packets per second. Here, higher is better. So let's take a look into the shared nothing solutions. One thing that pops out is that there are actually 2 NFs that don't have a shared nothing solution. The dynamic bridge because of hardware limitations, and the load balancer because there are some scenarios where every packet needs to access common state. But for all the others, all the other NFs scale linearly with the number of cores, ultimately being bottlenecked by the PCIe, which is an optimal scenario. All in all, we arrive at the conclusion that the shared nothing implementations scale linearly with the number of cores. Now let's take a look into the locked-based solutions. So this is, for the policer, this is what happens when every packet needs to write the state. The performance is abysmal. But on other cases, for example, for the dynamic bridge and the load balancer, they present as a very good alternative to shared nothing. All in all, the majority of the network functions, at least in a lock-based implementation, scale linearly with the number of cores, although in a less scalable way than the shared nothing ones. Finally, let's take a look into hardware transactional memory approaches. We can see that for very simple NFs, these are comparable with the lock-based implementations. But for all the other ones, they are otherwise unpredictable or worse than locks due to the high amount of transaction aborts. The main conclusion from these results is that the hardware transactional memory, at least for the NF domain, scales poorly and is very unpredictable in terms of performance. So wrapping this all up, I've presented Maestro, a push-to-parallelize system that automatically parallelizes software network functions. It generates share-nothing parallel solutions whenever possible and locked-based solutions otherwise. Maestro's share-nothing NF scale linearly with the number of cores. Thank you for your time. I'm happy to take questions.